board space. You'll have to start like halfway now, right?
Let's just do it on Snapchat.
Okay.
Hey, wait.
Did we complete the decon? We did one?
It's all like nuts.
Focus.
See, that's
There
why
we
I
go.
had it turned the other way around in selfie mode, which is a lower quality. But
I would have turned
it
it.
stops people from just like staring at the screen.
Yeah, I'm just gonna be like watching.
But I have temporarily broken my other phone.
You got two phones.
Oh, wow. Oh, shit. I was actually a little worried that my
Emily,
mouse keep like
tell me when I'm off screen.
You're off screen. I mean, you're way too high.
too high, yeah.
A little
Really high.
lower.
Good.
A little lower. Okay, right there.
This is not on the screen?
No.
I told you it showed like half of it.
Huh? I told her, yeah. Did you?
No. I looked online. Where's the menu?
I have a question. Can you laminate stuff in your oven?
Yeah.
Okay.
How much is it?
I'm not gonna charge. We usually don't charge people for it.
When do y'all work?
How about now?
You're on screen.
2. Right after today.
Okay.
We close at 5.
I might come by there Friday.
Okay.
After genetics.
I don't work that on Friday, but
Dang it. When do you work? Do you work on Friday?
Look how cute this is.
good job.
This is beta-keto ester. It is the product of the Claisen condensation, and of course it has alpha hydrogens. Tell me anything at all about those alpha hydrogens.
They're acidic.
Mm-hmm. Are they more or less acidic than the alpha hydrogens here?
More acidic.
More, because they're between two carbonyls. So we didn't put numbers to that, but an alpha hydrogen between two carbonyls, I know, have a pK of about 9. That's more acidic than an alcohol. Yeah. Okay, so we can do all the same reactions that we did previously. This is one of the things. You take the aldehydes or ketones, you make them into alpha beta unsaturated ketones with aldol. Still going to have alpha hydrogens. And then you take this, still going to have alpha hydrogens. So now we can continue, and we can do, guess what? You can make an enolate here, and then you can react anywhere. All right, so this molecule has three places for reaction. I got the alpha hydrogen. I've got nucleophilic acyl substitution right there. And I've got nucleophilic addition right here. Ketones react with nucleophiles by addition. Esters react with nucleophiles by substitution. Beta-keto esters can also react with base to do any of our enolization reactions. Okay, so we've got a bunch of stuff open to us. Today what we're going to do is look at molecules that have more than one functional group, and I'm going to control the site at which the reaction occurs. There's a lot of really nice chemistry that goes on here. There's a thing, it's in the notes, called malonic ester synthesis. It's really crazy, and it's very, very good. It involves making an ester and then decarboxylating this in a cyclic reaction. We're going to skip it this year. I'm going to do it. We could do alpha alkylations. We could do alpha halogenations. I could use this as the nucleophile to another ketone and have it do an aldol to that ketone. The whole world is open to it. All right. What if I wanted to selectively react at the ester? Let's say I wanted to reduce that ester so that instead of having a beta-keto ester, if I reduce an ester, what do I make? What's the reduction product of an ester?
An alcohol.
What kind of alcohol?
Enol.
Don't overthink it. What kind of alcohol? What flavors do alcohols come in? Primary, secondary, and tertiary. It's an ester. What type of alcohol is it going to be?
Primary.
It's always going to be primary because esters are always terminal group. Right? So here's my carbon. I'm going to reduce it to an aldehyde. I'm not going to stop at the aldehyde, although I'll do that next. I'm going to react all the way through to the alcohol. Okay? What's wrong? Okay, so what reagent would I use here? What do I use to reduce esters?
Tin hydrochloric acid.
It's one of the homogeneous ones. My two reducing agents of choice are lithium aluminum hydride and sodium borohydride. Sodium borohydride will not reduce esters, but lithium aluminum hydride will. Okay, that's what I want. However, that's not what I get. Lithium aluminum hydride is strong enough to reduce the ester and the ketone. Reduces the ketone to a secondary alcohol, reduces the ester to a primary alcohol. So I cannot use lithium aluminum hydride. What should I use instead? What if I use the sodium borohydride? What do I get instead? That's what I want. That's what I'm seeking. If I use if I use sodium borohydride, sodium borohydride is not powerful enough to reduce an ester, but it is powerful enough to reduce a ketone or an aldehyde. So I'm out of luck. I can't make this work. Sodium borohydride will not reduce esters. Lithium aluminum hydride reduces everything. So I have no option available to me. This doesn't work. The reason being, when we looked at reactivity towards nucleophiles, I know I'm going to be off screen there. Aldehydes are more reactive than ketones. Ketones are more reactive than esters. So no matter what I do, I'm starting with a keto ester. There's nothing I can do. The ketone is more reactive than the ester. There's nothing that I can mix this with that will react only with the ester and leave the ketone alone. That's impossible. We're going to do it today.
Shane. Check your phone.
Give it to him.
This.
Yeah.
So if I made this leave somehow, and well, it's a leaving group, so I have to replace it. What would I replace it with that would give you the answer that we're looking for? This is the molecule. You've been tasked to go make that. That's the problem. Your boss says, I want 5 liters of that on your desk, on my desk, by Friday. And you've got this. And none of your reagents will get you to that. They will get you to that or that, but not the one that you want. And the key to our success is also the key to our downfall. Aldehydes and ketones are more reactive than esters, which means that I cannot react just the ester. So, what I do instead, remember Helm-Bollard-Solinsky? The carboxylic acid was more reactive than the alpha hydrogen. So what I did was I distracted the carboxylic acid for half an hour, turned it into something else that I know that I can recover from, something that's reversible, and then I did my alpha halogenation. And then I turned my acyl chloride back into a carboxylic acid. So why need something that will turn an aldehyde or a ketone reversibly into something that won't react with the reducing agent? Leave this as the only site for reaction, and then reversibly change my stuff back to being a ketone again. What happens when you react ketones with alcohols? What do you make? What do you make? Come on, people. Ketone plus alcohol. Is there an electrophile in the room?
Yes.
Where is it?
Positive charge.
Is the electrophile here?
No.
No. That's a lone pair of electrons, which doesn't make it an electrophile, it makes it a
Nucleophile.
That's where the arrow comes from. Where does the arrow go to?
Carbonyl.
There's my nucleophile. There's my electrophile. What am I gonna? What reactions do ketones do?
Acid catalyzed.
Do they do substitutions? Do ketones do substitutions? Yes or no?
Nucleophile acyl substitution.
There's no leaving group. Ketone doesn't have a leaving group. Cannot do a substitution. It's not a nucleophilic substitution. It's what? If only it was written on the board behind my head.
Clayson.
Nucleophilic addition.
Nucleophilic addition of an alcohol to a ketone makes what named molecule? I know. What gets made here? Those of you that were in lab yesterday may hang your head in shame because that's what we did. Wrote on the board yesterday. Oops. Okay. What if I added another alcohol? What do I make?
Acetate.
Yes. Technically, they're ketals. Ketones make ketals, aldehydes make acetals. I am told, MCAT kind of a question, that in the future, they're all going to be acetals. There will be no ketals. Ketals will be relegated into obscurity because there's no need for two naming systems. Okay. If I recall correctly, all of that was in equilibrium. Ketone plus alcohol makes hemiacetal and acetal plus what? What's my side product? So, if I mix a ketone with a lot of alcohol, if I have excess alcohol, my equilibrium rides that way. At the end of the day, when I don't want my ketones to be acetals anymore, or ketals, I add lots of water. And the equilibrium pushes back and pops out my ketone again. This is a reversible reaction that will take the ketone or aldehyde out of this molecule, off the table, then we can reduce the ester. Let's do it. Just for fun. What does an acetal, hemiacetal look like?
An oxygen.
Tell me what's here.
R group.
What's here?
Oxygen. Hydrogen.
What's here?
R group.
What's here?
Another OH.
A what?
Another OH.
That's a geminal diol.
Damn it.
It's a diol. Two ols is an ol, there's an ol, there's two ols. Alcohol ether that are geminal, that's a hemiacetal. So what is an acetal? acetal is a geminal diether. I'm assuming this is off screen.
Yeah.
Okay, is this on screen?
Yeah.
Another OR here. All right, this is an acetal. It is all in equilibrium with my keto, and I can control. Add alcohol, go that way. Add water, come back this way. Okay? What if that R group and this R group were the same molecule? I'm going to use a diol to make an acetal that protects just the keto. Okay. I'm going to put this in a little bit of acid. And if I said ROH and ROH, then it wouldn't be too much of a stretch. See this? An acetal is a geminal diether. Right? Aldehydes, ketones, more reactive than the ester. So the ester doesn't do this. The aldehyde does. The ketone does. And I made a geminal diether, which is reminiscent of what we've done in the past. Okay, here's my alcohol. Instead of being CH3OH and CH3OH, instead of being that, because right now we can all understand this, CH2, CH2 with a bond between the two carbons. Using the chelate effect, having this molecule bond to the same carbon twice, I get a boost in entropy that allows me to do this, because I just kicked off 2 molecules of water in placing that diol onto the molecule once. Plus, there's an artificially high concentration. If I break that bond, if I chip away at that bond, it's still attached at this end, and therefore it's easy for it to reattach. This is stable, and it's a 5-membered ring. So I want this to be 1,2-ethane diol, or 1,3-ethane diol. I want to make the pentagon or the hexagon. Don't try to make a square, don't try to make a heptagon. Nature doesn't like that. Okay? Now, let's do the reduction. Lithium aluminum hydride. acid workup. Just reduced the ester, left the ketone alone. Add lots and lots and lots of water, and you get your ketone back. So what I've done now is a selective reduction. And what's gone on at the active reaction step is this is what we call a protecting group. And there are multiple protecting groups in the book. Actually, that's not really true. There are multiple protecting groups in use in modern synthesis. No organic chemistry textbook does a good job of collecting them together. We need a chapter. We need a chapter that just says protecting groups. There's a thing that gets used a lot, silyl ethers, to protect alcohols. This is a big one, and because it's in this chapter and it's relevant, we're going to use it. So you could, if I had an aldehyde here, and I had an ester there, we could use this same strategy to make the dialdehyde. What would we have to do differently?
Put it in the water.
Do you have to reduce or oxidize alcohol?
I just protected the aldehyde. The ester is still exposed. Now I need to reduce this ester to an aldehyde. How do I do that? It was on the last test. And almost everybody got it right. Ester to aldehyde. Esters can be reduced to aldehydes, but of course aldehydes are more reactive than esters. So if I reduced an ester with lithium aluminum hydride to make the aldehyde would react with the lithium aluminum hydride immediately and go on to make the primary alcohol. So instead of using lithium aluminum hydride, I use diisobutyl aluminum hydride instead. That gives me the aldehyde, stops the reduction of the aldehyde. Now, because we're here and we've just done this, it opens the door for us to show you a quirky little side reaction that happens instead. I don't believe it's in your book. If it is, I can't find it. People don't do it and don't talk about it because it stinks. But I talk about it because I love stinky chemicals. Plus, my followers for nice sounding named reactions. And this is the, in my opinion, second best named reaction. I'm going to take this beta-keto ester, and I'm going to turn it to that. Oh, no, because this is back to being ketone. Yeah, this is back to being ketone. That. This is ethane diol. Yeah, I'm going to make this an arrow, not an equilibrium. If I replace the oxygens with the atom that's below oxygen in group 6, 16 if you're an inorganic chemist, with sulfur, I make 1, 2 ethane dithiol. Thio, in a word, means find the oxygen and replace it with sulfur. So ol means alcohol. Thiol means replace the oxygen in an alcohol with the sulfur. And this is a dithiol. So find both oxygens in a diol and replace them both with sulfur. Alcohols, we know what alcohol smells like. It smells clean, sharp. It has a certain freshness to it. Diols smell sweet. They're antifreeze. Dogs love antifreeze. Bad news for dogs? Kidney failure. This causes kidney failure, and but it's really super sweet. And so if there's, if you have a leaking radiator, you need to hose that down and not let your dog anywhere near it, because they love to lick that stuff up, and then there's not really much of an antidote for it. They usually die. Replace those oxygens with sulfur, and this smells like poop. Like really, really, really bad. This is the worst smelling chemical I've ever smelled in my entire life, and I've smelled lots and lots of chemicals. I did a couple of years of several years of sulfur chemistry. And it clings to you. So this smells like undescribably bad poop smell. Like, what were you eating? Onions? Like for a month? Onion only diet. Really, really bad. And it clings to your clothes and your skin and inside your nose. So even after you go home and you scrub yourself clean so that when you go out to your fish fry barbecue down the pub. You don't smell like poop. You still think you do because it's stuck to the hairs inside your nose. And yeah, it's
You gotta shave your nose hairs.
I feel like you should put that on a test. Unless you want.
What's the
What smells like
stinkiest
poop?
chemical?
Smells like poop.
I love this chemical. I really, really do. But it's so bad. All right, go ahead and do the dibal thing now. I turned my ester into an aldehyde again. And now, I'm not really gonna be able, if I hydrolyze that off, I might just be able to reform the carbonyl. But instead of hydrolyzing it off, I'm gonna reduce it off the old-fashioned way with rainy nickel. And when you do, it puts the hydrogens back on the poop-smelling molecule, which then floats away. And so there was no oxygen reintroduced into this molecule. It strips the oxygen out. This is a decarbonylation. And it's named after the guy that discovered it. His name was Mozingo. Coming in at number 2. No pun intended. Is the Mozingo. But holding steady at number 1.
Chichi
You
bun.
say it with chichi bacon. Now, there is a way, it's in the notes, and you can go find it if you want it. There is a way to make all of this go away and just leave. In fact, take that carbon with it. In a decarboxylation, it's called a malonic decarboxylation. It's a beautiful little piece of chemistry, but I've opted not to touch it this year. Okay. All right, that leaves us with biomolecules for the remainder of the term. Let's get started. Oh, no, it doesn't. Denied.
Dang it.